Now that we know how to use Pluto notebooks, it's time to put our newly acquired skills to use. Today, we're going to embark on our journey to learn how to solve differential equations in Julia by using the differentialequations.jl package and Pluto notebooks. Just one small problem. I have never taken a differential equations class. If I don't know anything about differential equations, will I be able to figure out how to solve them using Julia? Well, let's find out. Welcome to Doggo.jl, where I explore the vast Julia wilderness and turn my discoveries into wholesome Julia tutorials. Spoiler alert, knowledge of differential equations is not required for this tutorial. You only need to know some basic math. Otherwise, I'll cover any math that you need to know. But I am assuming that you've watched the first 3 episodes of this series, so I'm assuming that you know how to use Pluto notebooks and that you know the basics of the Julia programming language. With that said, let's get started. Rather than starting with a lengthy exposition about concepts and terminology, let's jump right into a real example of a differential equation. We'll learn concepts and terminology along the way. In this example, we're going to look at how to solve the problem of continuous compound interest. Way back in 1683, Jacob Bernoulli was pondering the magic of compound interest. Here's a modified version of the thought experiment that he was conducting. Imagine that you deposit $1 into a bank account, or whatever your local currency is, and imagine that this bank pays 100% interest per year on your deposit. So, if the bank pays interest once per year, then your account balance at the end of 1 year will be $2, since you have $1 from your original deposit, plus $1 more for the interest payment. Now, suppose the bank pays interest twice per year. After 1 year, what will your account balance be? Well, it should be some number greater than $2, since you'll receive a partial interest payment after 6 months, and then you'll earn interest on that interest for the next 6 months. Now, let's repeat this thought experiment for interest payments every quarter, or every month, or every week,
or every day,
or every hour,
or every minute,
or every second.
As you shrink the time in between interest payments, your account balance at the end of the year keeps getting larger, because you keep earning interest on interest in greater frequency. If you could somehow keep shrinking the time in between interest payments, what's the maximum amount that your account balance can be after 1 year? In order to calculate that, you would need to shrink the time in between interest payments to be infinitely small, the smallest number that you can imagine without it being 0. That way, the interest payments could compound in a continuous stream without any interruption. So back to our thought experiment. Let's say you deposit $1 at the beginning of the year in a bank that pays an interest rate of 100% per year, compounded continuously. In this scenario, what would your account balance be at the end of 1 year? Well, we know that the ending balance will be some number greater than $2, but how much greater? Will it be $3? $5? $10? $100? Regardless of what the answer is, you have to admit, it's an intriguing question. This question gets to the heart of differential equations. The continuous compound interest problem is an example of a differential equation. A differential equation defines how something changes with respect to something else. So in this example, our differential equation defines the relationship of how our bank account balance changes with respect to time. If we can solve this problem, then we'll be able to predict what our bank account balance will be at any given time. So, how do we solve this? Well, we know that it's possible to solve this problem by hand, since Bernoulli solved it by hand back in 1683, long before computers were invented. If you take a differential equations course in school, they'll teach you how to solve differential equations by hand. But we have computers now, so can't we just use computers to solve differential equations? Well, let's find out if we can solve this problem in Julia by using the differentialequations.jl package and Pluto. A new version of Pluto was released recently. If you see a pop-up notification about it, you can update Pluto in the package manager by typing in Update Pluto. I've already updated my version, so there's really nothing to see here, but that's how you would do it. After updating Pluto, you can launch Pluto from the Julia REPL. Next, let's create a new notebook and title it Continuous Compound Interest. This is optional, but I'm going to customize this user interface like I did in the first tutorial. Let's save this file by using the Save Notebook bar at the top. Next, let's add a few packages. The differential equations package and the plots package are both large packages, so it may take a few minutes to load everything. Now that everything's loaded, let's describe the problem that we're trying to solve. The continuous compound interest problem is an example of an ordinary differential equation, or ODE. Here, the word ordinary simply means that we're trying to understand how one thing changes with respect to something else, as opposed to how two things or more are changing with respect to something else. Here's a generalized version of an ODE. The left-hand side of this expression is read the derivative of u with respect to t. U is the unknown function that we're trying to understand, and t is time. It doesn't have to be time, but in most practical cases, we'll be interested in understanding how things change over time. On the right-hand side is p times u, where p stands for any parameter that alters the function u. When it comes to the differentialequations.jl package, it expects the ODE to be defined in terms of a Julia function that takes the arguments u, p, and t. In our continuous compound interest problem, u is the bank account balance, and it's a function of t, or time. And p is the interest rate, since it's the parameter that alters the function u. In its most basic form, this is how the differentialequations.jl package understands a differential equation. We can use this to define our Julia function. The next thing we want to do is to assign values to the variables u, p, and t. When it comes to u, all we need is the beginning balance at time 0. So if we want to recreate Bernoulli's thought experiments, we need a beginning balance of $1. As an aside, I know that both Julia and Pluto support Unicode in actual code. For example, you could use a subscript here. But whenever possible, I try to write code that is agnostic to the programming environment. Since not all programming environments support Unicode, I try to avoid using it in my actual code. But you do you. If you like Unicode, then by all means, go for it. Now, getting back to the beginning balance. Normally, when using the differentialequations.jl package, this would be all you need for the beginning balance. But since we're using Pluto, let's bind this variable named u_begin to a Pluto UI slider widget, so we can adjust the beginning balance later on. This slider will allow us to change the beginning balance from $1 up to $1,000. Next, we need to assign a value to P, or the annual interest rate. In order to recreate Bernoulli's thought experiment, let's use a value of 100% per year, which is just 1. Now, just like the beginning balance, let's bind this variable named P to a slider, so we can adjust the interest rate later on. This slider will allow us to change the interest rate from 1% up to 100%. Next, we need to assign the variables for time. For time, we need a starting time and an ending time. These values need to be placed inside of a tuple assigned to a variable named tspan. In order to recreate Bernoulli's thought experiment, let's use a starting time of 0 and an ending time of 1. Now, just like the beginning balance and the interest rate, let's bind the variable for the ending time to a slider so we can adjust the time span later on. This slider will allow us to change the time span from 1 year up to 50 years. Next, we need to define the ODE problem for the differentialequations.jl package. The differentialequations.jl package contains a function appropriately named ODE problem, which takes 4 arguments. The first argument is the function that we're trying to solve, which must be a Julia function that takes the arguments u, p, and t. The second argument is the value of the function at time 0. The third argument is the time span in the form of a tuple containing the beginning time and the ending time. And the fourth argument is for p, which stands for any parameter that alters the function u. Now that we've defined the problem, we can solve it by using the solve function from the differential equations package. I know it doesn't look like much, but this output is the solution to our differential equation. The first column contains some values for time, and the second column contains values for the bank account balance at those timestamps. So at time 0, the account balance is $1, which is just our original deposit. And at time 1, the account balance is around $2.72. So now we know the answer to the question, what's the maximum amount that your account balance can be after 1 year if your beginning balance is $1 and your bank pays interest at a rate of 100% per year, compounded continuously? It turns out that the maximum amount is around $2.72. Now, it's a little difficult to tell what's going on with the solution just by looking at these numbers. Fortunately, the differential equations package is tightly integrated with the plots package, so plotting the solution is extremely easy. So, what are we looking at here? Since the values along the x-axis go from 0 to 1, the x-axis must be time. Plus that little t kind of gives it away. And since the values along the y-axis go from 1 to around 3, the y-axis must be our bank account balance. It's a little hard to see on this plot, but this is not a straight line. It's a slight curve. Let's add some attributes to our plot recipe in order to make this plot a little more presentable. This plot is the visual representation of the solution to Bernoulli's thought experiment. As you can see at time 0, the bank account balance is $1, which is just our original deposit. At first, the account balance grows slowly due to the infinitely small interest payments. You can imagine a straight line going from time 0 to time 1, with the bank balance going from $1 to $2. But as time goes on, the account balance grows more rapidly, since the account is earning interest on interest. It takes about 70% of the year for the account balance to increase by $1. But then it shoots up another 72 cents in the last 30% of the year. At the end of year 1, the account balance reaches around $2.72. That's $1 for the original deposit, plus $1.72 in interest payments. You can see the solution that the differentialequations.jl package estimated for any time t by using the variable named SOL, immediately followed by parentheses. Does that number look familiar to you? Doesn't that look like Euler's number? Coincidence? Of course, this is not a coincidence. This is the definition of Euler's number. Euler's number is the answer to the question, what will your bank account balance be after 1 year if your beginning balance is $1 and your bank pays interest at a rate of 100% per year, compounded continuously? The answer is 2.718 ... which is an irrational number that we know today as Euler's number. So here's a fun fact. Euler's number wasn't discovered by Leonhard Euler. It was discovered by Jacob Bernoulli in 1683, while he was studying this very question about continuous compound interest. So why is this number important? It's important because this observation about how the bank account balance grows with respect to time can be generalized and applied to understanding how things grow organically in nature. So you can replace the beginning bank account balance with any beginning quantity at time 0. And you can replace the interest rate with any continuous growth rate per unit of time. So if you start with a beginning quantity of something of 1 at time 0, and that something is growing at a rate of 100% per unit of time, then the quantity of that something at time 1 will always be 2.718, regardless of what that thing is. Pretty wild, right? But this isn't the end of the story. The value that the differential equations package estimated for our account balance at time 1 raises some issues that we need to better understand. You can see the value for Euler's number that's built into Julia by using \Euler tab. As you can see, our estimated value for Euler's number is pretty close, but it's not exactly the same as the constant built into Julia. It turns out that solving differential equations using a computer often results in a slightly different answer compared to solving differential equations by hand. For starters, a computer uses floating point math, which is, by its nature, less precise than solving problems by hand. Secondly, a computer solves differential equations by selecting a subset of timestamps to solve, and then it extrapolates the values in between the timestamps. As a result, you can almost always find a solution to an ordinary differential equation using a computer, but that solution will be an estimate. Now, this estimate is accurate enough for most practical applications, but it may not be accurate enough for theoretical work. So those are some things to keep in mind when using a computer to solve differential equations. But before you give up on using your computer to tackle these types of problems, consider the added benefits of being able to use your computer for modeling, simulation, and analysis. For this demonstration, let's pull our sliders down to our plot so we can adjust the variables. As you can see, the plot updates automatically as I move the sliders. But it's a little difficult to understand what's going on because the scale along the axes keep changing. Let's lock the ranges for the axes by adding a couple more attributes to our plot. Now when we move the sliders, the curve will be the only thing that changes in the plot. Let's go through a few scenarios to see what we can learn from this plot. Let's set the interest rate at 1% and set the years to 50 years. Let's keep the beginning balance at $1 and let's add some markdown to display the ending balance. So if we deposit $1 into a bank that pays an interest rate of 1% per year compounded continuously, it looks like our ending balance will only be around $2 after 50 years. Now, watch what happens as I change the interest rate. At some point, the bank account balance explodes, so that it becomes too large for our computer to calculate. Now, let's set the interest rate to 10% per year. If we keep our beginning balance at $1, after 50 years at an interest rate of 10% per year compounded continuously, it looks like our ending balance will be around $148. Now, let's try increasing the beginning balance. So, if we increase the beginning balance to $1,000, then our ending balance will be around $148,000. You can see how this model can be useful for answering what-if questions. For example, what if we start with a beginning balance of $1? What interest rate would we need in order to reach an ending balance of $1 million after 50 years? It looks like we would need an interest rate of roughly 28% per year compounded continuously. Unfortunately, there's no bank in the world that pays interest at 28% per year, whether it's compounded or not. Now, what if we had a beginning balance of $1,000? What would the interest rate need to be in order to reach $1 million after 50 years? So it looks like we need an interest rate of roughly 14% per year compounded continuously. Again, there's no bank in the world that will pay 14% per year compounded continuously for 50 years, but in theory it's possible if you can find a bank willing to pay that much interest. You can use the year slider to see how the ending balance changes over time. As you can see, in the early years, the account balance grows slowly, but after some point, the growth becomes explosive. This growth curve can be seen all throughout nature, which is why this is such a fascinating problem to study. This is really amazing, right? With this one model, you can simulate an infinite number of scenarios. You can literally spend hours just playing with this model and asking all sorts of what-if questions. And of course, the questions don't have to be about continuous compound interest. The questions can be about how anything grows over time, given some continuous growth rate and a beginning quantity. Now that you have a working model for continuous growth, you can accurately predict the quantity at any time t. I think it's important to note that this knowledge isn't coming from some external dataset. It's being extracted from this one innocuous-looking differential equation. How is that even possible? This differential equation is like some magic bean that can sprout some gigantic beanstalk of knowledge. This will be a recurring theme for the rest of this tutorial series. Differential equations are not like other math equations. On the surface, they may appear deceptively simple, but once unlocked, they can reveal some of the most fascinating secrets of the universe. So I think I answered the question, if I don't know anything about differential equations, will I be able to figure out how to solve them using Julia? Thanks to the differentialequations.jl package, the answer is yes. Now in fairness, today's example was the easiest example of a differential equation. But if we can figure out how to solve the easiest example, then what hope would we have for solving more complex problems? At least now, we have some hope. But there are some pros and cons to consider when comparing solutions to differential equations solved by hand or solved with a computer. A solution to a differential equation solved by hand is called an analytical or symbolic solution. Analytical solutions are more accurate, but it's not always possible to find an analytical solution. A solution to a differential equation solved using a computer is called a numerical solution. Numerical solutions are generally less precise, but there's almost always a numerical solution to a differential equation. But the accuracy of numerical solutions are considered good enough for most practical applications. Plus, what you get in return for a numerical solution is an extremely powerful computer model that can be used for simulations and for analysis. Over the next several tutorials, we'll continue to explore how to solve many different types of differential equations. So stay tuned for the next exciting episode. If you made it this far, congratulations! If you enjoyed this video and you feel like you learned something new, then please consider smashing that like button, leaving a comment, sharing this video, and subscribing to this channel. If you'd like to support the educational work that I'm doing, please consider making a purchase at the Doggo.jl online store. You can browse through a wide selection of Doggo.jl merch by clicking on the Store tab. For one-time donations, please consider using the Super Thanks button. For ongoing support, please consider joining and becoming a channel member. Channel members get early access to all of my new videos. Early access videos do not contain YouTube ads. New tutorials are posted on Sundays/Mondays. Thanks for watching, and good luck on your Julia journey.